Hello everyone, this is part 3 of simple linear regression where we're going to interpret the results and talk about various potential problems with the results. Let's pick up from part 2 starting from this equation with 30 data points. From here, we wanted to minimize the sum of square prediction mistakes using B0 and B1, and after calculations, we found the B0 and B1 that achieve our goal, which we call beta 0 hat and beta 1 hat. And after plugging in the numbers using 30 data points that I fabricated for this video, we got these numbers for beta 0 hat and beta 1 hat. So these numbers are the OLS estimates. And finally, all of this led to the fitted line, which we call OLS line. Also, we can express any particular student I's exam score with respect to hours studied by using the two beta estimates and the residuals. So U hat I is simply a notation representing residual for student I. Okay, so then now we're going to get into interpreting all of these results. For sake of interpretation, we're going to assume that OLS estimates are reliable, meaning we interpret the estimates for what they are and not worry about various issues that may confound the interpretation of estimates. Of course, we'll talk about the issues or problems later on. Okay. Let's begin with prediction of exam scores. Note that prediction can be done using this equation, which says that y hat, which is a notation for predicted y, or predicted exam score in our case, equals the estimated intercept plus estimated slope times some x value. So y hat is essentially the same as the y values of the OLS line you're seeing on the page. The equations here are the same as the one you see on the top right corner of the screen. Also note that the variable x doesn't have I subscripts. That's because we can plug in any value of x to get the predicted scores. We don't have to use the x values taken from the data. Now, using all of this, we can say that, for example, if a student studies 4.5 hours, then on average, the exam score is predicted to be 0.636 out of 1. So what I did here is I simply plugged in 4.5 into the equation of the OLS line, and the predicted score is somewhere close to 0.64. And on the graph, the prediction is right about there. Note that in your interpretation, you want to include the term on average, because if some number of students study for 4.5 hours, not all of them are going to get exactly 0.636. What about 20 hours? Well, according to the Econometrics model or the equation, we can say that if a student studies 20 hours, then on average, the exam score is predicted to be 1.38. But remember that since the maximum score is 1, getting 1.38 is not possible in reality. So if I trust the Econometrics model that we came up with, I would personally say that if someone studies for 20 hours, the score is predicted to be somewhere around 1. Okay, so you gotta be careful in the interpretation sometimes. Now let's get into interpreting the estimated coefficients, the beta 0 hat and beta 1 hat. We'll interpret beta 0 hat first. So what does 0.42 mean? 0.42 is the intercept of the OLS line, so it means that if a student studies 0 hours, then on average, the exam score is predicted to be 0.42 or 42%. What about beta 1 hat? What does 0.048 mean? Note that this is the important one since 0.08 is the estimated coefficient corresponding to the variable of interest, which is hours studied in our example. Since 0.048 is the slope of the OLS line, we can say that each additional hour of studying on average is predicted to increase exam score by 0.048. Now, if you think about it, this interpretation is a powerful statement because the estimate 0.048 is telling us about the causal relationship between exam score and hours of studying. It's saying that additional hour of studying causes exam score to increase by about 0.048. If this is true, then this is a valuable information to schools, to parents, to students, for example, who are about to take the exam. Note that here, it was easy for us to take 0.048 as the causal effect simply because we assumed that to be the case. We decided not to worry about the potential issues that may confound interpretations. Unfortunately, in reality, finding a causal relationship between two variables is a difficult task in many cases. I'll briefly go over an example how we may have misinterpreted the causal effect of our study on exam scores. To see one potential problem, we're going to consider an additional variable. First, suppose that higher IQ also leads to higher scores. And also suppose that students with higher IQ tend to study for more hours. Okay, so then in this new scenario, if we consider two variables, then it's not correct to say that all of 0.048 is the positive effect of studying on exam scores, because 0.048 also includes some positive effect of IQ on exam scores. Intuitively, one way to understand what's going on is to look at this region as an example and ask how the students in this region achieved high exam scores. If you believe that studying increases exam score, then you want to say that studying more hours had something to do with the fact that this group of students got high scores. But since these students are likely to have high IQs, you should think about how having high IQs also had something to do with high scores. So what all of this means is that the true isolated causal effect of our study on exam scores may actually be represented by this flatter line, which is saying that the isolated causal effect of our study is something lower than 0.048 if we actually take into account the effect of IQ on exam scores. When I say taking into account the effect of IQ, I'm saying holding IQ constant. In other words, the causal effect of our study only by itself when IQ is not changing is going to be something lower than 0.048 in this scenario. By exactly how much lower is the true effect of our study in comparison to 0.048? Well, to answer that question, we have to do whole new calculations. The bottom line in this new scenario is that 0.048 does not accurately represent the causal effect of our study on exam scores because we didn't account for IQ's effect. We left out IQ in the calculation. So one lesson of this example is that if your boss asks you to analyze how Y is affected by X, you don't want to make conclusions just by looking at a graph like this that simply shows Y and X. You can rely on graphs like this to get a rough idea, but if your goal is to find the causal effect, you definitely need to take into account various issues before making a conclusion. Okay, at this point, I want to make it clear that the data is not real, so you shouldn't take any of the result here to be a fact. I'm simply using made-up data and examples to show how to interpret OLS estimates and also show how there can be problems with interpretations. Alright, let's now conclude by going over the big picture here. We began with this equation for Y and X, and we have 30 students in our data. We computed the OLS estimates that minimize sum of squared prediction mistakes. And so now we can express any one of 30 exam scores using this equation, and we can also come up with predicted exam scores using this equation. Beta 1 hat, the main estimated coefficient of interest, can be interpreted by saying each additional hour of studying, on average, is predicted to increase exam score by 0.048, or almost 5%. We also saw that there can be many ways that may confound the interpretation of OLS estimates. For instance, having a small sample size like 30 data points in our example may lead to problems. And we already saw that leaving out important variables in the calculation can also lead to problems. Figuring out when there can be problems, estimating the magnitude of the problems, devising methods to eliminate those problems, and so on are the meat of econometrics. This is where econometrics gets hard and interesting. Some economists spend their entire career trying to figure out ways to come up with more reliable OLS estimates, which among other things is going to help to identify causal effects. And some of them have won Nobel Prizes for their work. In the next videos, we will begin to test statistical reliability of our results. If you do not have a firm understanding of statistics, then the next videos may be difficult for you.